Hello everyone. In this video, I'm going to discuss about prime mover. Okay. Now, let us first talk about what is a prime mover. A prime mover is an initial source or of motive power such as windmill, water wheel, turbine, or any internal combustion engine designed to receive and modify force and motion as supplied by some natural source and apply them to drive a machinery. As you can see from this block diagram, we have some source of energy like hydro and wind energy and some other sources. It will be the source will be received. It is the source of energy that will be received by the prime mover, and the prime mover will modify the force and motion supplied by this source and apply them to drive a machinery, right? Which in this case, electric generator. So there, the prime mover and the electric generator, they are coupled together so that when the prime mover rotates, let's say in clockwise direction, the generator will rotate and generator will convert mechanical energy into an electrical energy. Prime mover is very, very important in power generation. So I have here some application of prime mover. We have an hydroelectric power plant. The water is going down here and it will try to rotate this prime mover. And then it is coupled to the generator, and generator will convert mechanical energy into an electrical energy, supplying power to the consumer. Now, we also have a thermal power plant, right? We have the steam generated by the thermal power plant. Sometimes we have, it can be a natural steam in some part of the world. So it will go to the steam turbine. So a steam turbine will rotate and it is coupled to the generator and it will produce electricity. Also the same with the wind power plant. We have here the turbine, right? The propeller and connected to the generator, which is this is the generator. Okay, and it is connected to a transformer to transmit power to the consumer. So there is what you call friction, which is opposition to the motion. A friction is the resistance to motion due to sliding, and all machineries consume frictional energy because their parts slides against one another. In short, friction is a force that always opposes the motion. Now, let's talk about the prime mover now. Prime mover in 4-quadrant dynamometer power supply is basically a DC motor that operates like a linear voltage to speed converter. What does it mean? So here is an example of a DC motor. So I will connect, these are the carbon brushes here. If I'm going to connect a positive voltage, a positive here and negative here as a source connected to the brush. So let's say the DC motor will rotate in clockwise direction. So as I increase the voltage, the speed also increases, right? As you can see here from our graph. The direction, another thing that you should consider in the operation of prime mover is the direction of rotation. It's directly related to the input voltage polarity. A positive voltage produces a clockwise rotation, and a reverse input voltage polarity will cause the prime mover or the rotor of the prime mover to rotate counterclockwise direction. We called it negative rotation. So counterclockwise is a negative rotation. Clockwise is a positive rotation. Okay. Of course, also that the speed is again voltage relationship is a straight line, and the higher the applied voltage, the faster the motor turns. Okay. Now let us try to observe the parts of the DC motor. And as you can see here, we have this brush, right? This causes friction also. Let's say our rotation is in clockwise direction. Okay, we have we have here a brushes. It causes friction, so we have a friction due to brush, carbon brush, right? And also there is a friction due to there is a bearing here. So this bearing, right? So if it is our direction of rotation clockwise, the direction of friction here is counterclockwise. So we have friction due to bearing. And there are two bearings here, one at the in front, of course, and one at the back. And so another cause of friction here is the wind friction. So if you try to rotate here, there is a wind effect. So we can say windage friction. So these are it is measured as torque. These are the torque. We can call this oppositional torque that opposes the motion of rotation. Now, the motor must overcome all this opposition torque in order to start rotating, because if the generated torque of the motor is less than the oppositional torque, it will not rotate, right? Suppose, let's say, for example, as we know that the voltage and the speed are linear, has a linear relationship. If the input voltage is not enough, it's very less, it will generate a torque that is not yet sufficient, so there will be no rotation. Let's try to try if we can play this video, this DC motor. Now, we are going to have a separate topic about DC motor, but as an advanced information for you, there are two connections in the DC motor. That can be series connection. As you can see, this is the battery, right? It is series with the field winding. This is the field winding, right? And the field winding will create magnetic flux according to the magnitude or the level of the voltage. So the higher the voltage, it will create a higher magnetic field, and the faster this rotor. This is the rotor. This is the rotating machine, and these are the carbon brush. So as the torque, suppose we are going to put a torque load on this motor, right? Like in washing machine, the higher the torque load, the speed will be reduced, right? It will reduce at this point. Unfortunately, for series motor, the draft of the torque is very large, right? It will drop very large. But there is another connection which we call shunt connection. Shunt connection. Let's see. Another connection is a shunt connection. Okay. This shunt connection, as you can see here, as we apply the torque, it is a little bit more constant speed, right, compared to the series motor, right? So we are going to discuss about it in our topic about DC motor. So look at the winding here. Field winding is parallel with the DC voltage source. Okay, this is shunt. So shunt means parallel. Okay. Next. So let us analyze when the prime mover is not coupled to any machine, right? When the prime mover is not coupled to any machine, let us put our analysis in equation a while ago. Let us again look at this diagram. We have, this is the rotor of the prime mover. We have a bearing friction from two points here, from front and back, and we have a brush, right? We have a brush friction and also a windage friction, right? A windage friction. So all of this are equal to the torque to be carried by the prime mover. It must overcome all of this torque in order to have a rotation. It must be greater than this. As is noted here, to have a rotation, the input torque must be greater than the torque friction of the prime mover. So we have an equation, TF prime mover is equal to T brushes plus T bearing plus T windage. And this is what you call a not corrected torque. Again, this is what you call not corrected torque. So T brushes, the torque that opposes rotation results from the brush friction. T bearing, friction due to bearing friction. T windage is a friction due to windage. Okay? And of course, to summarize, the torque opposition must be equal to the torque friction of the prime mover, and it must overcome the prime. In order to have rotation, it must overcome this value of oppositional torque. Now, suppose we connected a load into a prime mover. Suppose this is my prime mover. I connected a machine, a rotating machine, right? So how are you going to analyze now? We have already a friction inside. Inside here we have three friction prime mover, which is inside the machine, right? As we discussed a while ago. Plus we have another friction which is due to belt friction, right? If our rotation is also in this rotation, the belt friction is also opposing, right? Opposing this rotation. And also we have the torque opposition of the machine itself, The same thing that we analyze the prime mover torque friction we have in the machine, there is also a torque, right? And that if we add all of them, the T opposition is equal to TF prime mover, TF belt, plus TF opposition of the machine. And this is what you call a not corrected torque. Okay? TF prime mover, TF belt, TF of the T opposition of the machine. Now, the T opposition is larger, of course, when rotating machine is coupled to the prime mover. Of course, it is obvious. We have additional source of friction, so the T opposition will be larger compared as before when it is not coupled to another machine. Now, to have the rotation, again, the input torque of the prime mover must be greater than the T opposition. It must be greater than all of this torque opposition in order to have a rotation. Okay, now we need to know the torque opposition of the machine itself. This is the machine. This is the machine under test. This is the equipment that we are testing. We are testing the torque of this machine. So T opposition, again from this equation, T opposition of the machine is equal to T opposition minus, so just this part of the equation here, this part of the equation here, we will just put it in the other side, so it will become negative, minus TF prime mover plus TF belt, and this is what you call torque corrected, right? And in the screen of the 8960, you can assign measure T corrected, T not corrected. So again, the total torque opposition, the T opposition of the machine is equal to the corrected torque that can be viewed from lab bolt data acquisition metering or from the panel, the screen panel of the 8960 model. So now this is what I'm talking about. This is the panel board, the panel screen of the screen of the 8960 model. This is the front panel, right? Let me just orient you with the parts of this panel. We have the function button. This is the very important for controlling or setting up the screen of the funnel, and also the command. These are the two important control, okay, for this port quadrant dynamometer power supply or 8960 model. So it can operate in two modes, as a dynamometer. It can operate as a power supply, right? And a power supply, of course, you are to obtain output from here. You can generate a DC voltage here, so you can obtain here if you want, if you need to have a variable DC voltage source, so it can be obtained from here. But the operating mode in prime mover unit, the unit becomes a 4-quadrant dynamometer that can act as either a brake. When we use it as a brake, we can use it as a mechanical load, or we can use it as a prime mover to, or a motor drive to drive another motor, right? So as power supply, the unit becomes 4-quadrant power supply that can act as a DC voltage source, DC current source, and also AC power source. So, and here we have some also, if we want to connect it to the our lab volt data acquisition, we can connect this. This is the torque terminal. You have to put a wire here and the speed, and of course we need to connect the analog ground. This is the analog ground. Okay, and this is the power input button. And start stop, you need to start the rotation of the machine. You need to press start, and you can stop also. So you can see here clockwise prime mover brake. So we can change also this one every time we change the function. I'm going to show you on next slides. But before we go to that slide, let me just explain to you again. The direction of rotation of the prime mover is selected using function button. So this function button, we are going to use this to select the direction of rotation of the prime mover of the machine, right? The rotation speed of the prime mover is set by using a speed control or the control knob. So where is that control knob? This one. We can set the speed, we can set the torque, right? So a digital display on the 4-quadrant dynamometer power supply allows direct reading of both speed and torque. So it will be displayed here. This is the digital display. An analog output torques and speed of the 4-quadrant supply can be connected corresponding to the inputs of the data acquisition module. Okay. This is our data acquisition. It's connected to the computer. As you can see here, there is a torque, right? And here also there is a torque here and the speed. So you can just connect it here, and you can just connect this one there, right? And of course, you need to connect the ground to the analog ground also here. This is the analog ground. And of course, this one is connected to the computer. So you can see the torque also in the metering window, and you can also see this from here. Basically, we will use the for the metering window as our counter checking the values, and we can also obtain the measurement from here. Now, this is what I am talking about. The two modes are available to control the function which the 4-quadrant dynamometer power supply performs. It can be manual and the computer based, right? So let's say, for example, now we are going to operate this machine. This is the front panel this side. So I just captured it from here. I took this part just to explain to you. So we are now in a dynamometer. So now our first is when we initially this is the initial setup of the machine. It is on the clockwise prime mover or brake. So it is on the clockwise prime mover brake. And then we know clockwise is what? Clockwise is this one, and it is a positive direction. And counterclockwise is a negative direction. So remember that. So clockwise is positive, counterclockwise is a negative direction. So if I press this again, if I press this button, let me just put, if I press this button, it will give, okay, by the way, what's the meaning clock CW prime mover brake? CW prime mover brake, clockwise direction, used to operate a motor or a generator to a clockwise direction. So if I have this connection here, I have the connected to the motor, I have a clockwise direction, clockwise, and of course all the friction are, this is the frictional force, right? But the rotation will be clockwise. So clockwise prime mover brake. If I press this function, I will have another screen which is counterclockwise prime mover brake. It has the same function, but the only thing here, if you go here, it will rotate in another direction, which is counterclockwise. Okay, the same function as number 1, but it is on the clockwise direction. Again, if I press this one, I will have another screen, clockwise constant speed, prime mover, CWCS. So clockwise constant constant with prime mover brake. So again, it has a constant speed on this direction, right? Constant speed, and the closed loop under any varying load, under any varying load, it maintains the speed because of the closed loop control on this the 8960 model. So again, if I press this, so this is clockwise constant speed. So next it will be counterclockwise constant speed, right? The purpose are the same, constant speed, but in this opposite direction. Okay, opposite direction. So counterclockwise, right? If I press this again, I will have positive constant torque brake. So if it is mentioned here, positive constant torque, CT means constant torque. Of course, positive means the rotation is clockwise. So it can have a constant torque regardless of the speed, right? So if I press this again, if it is positive, the next screen will be negative. By the way, you have to be aware that here you are going to set the torque, right? You're going to set, we have a constant torque. We can set the constant torque here. Let's say a constant torque that we want to apply is 0.1 Newton meter, right? But if the actual torque of the machine is, let's say for example, 0.08 Newton meter, so that means it is less than the torque of the constant speed. So what will happen? The effect is that because this is very, very powerful, your source is very powerful, it will bring this motor into a maximum speed, right? If the load created by the opposing torque is smaller, so if this one has a smaller torque compared to the source compared to the prime mover, it will bring you to the maximum speed because this is very powerful, right? So you have to take note of that. Maybe you might wonder, oh, why I am in the maximum speed? So you should know. Now, again, I will press this. So I have a positive constant torque. I will now have a negative constant torque. Negative constant torque should be counterclockwise, CCW, right? Similar function. And lastly, if I press this again, this one here, I will have a 2Q constant torque brake. So I'm going to use now this one as a dynamometer. If I want to use dynamometer, okay, dynamometer. So if I'm going to use this as a mechanical load to another machine, let's say this one, I have put a DC motor. I want to test how powerful is this motor. I'm going to use this as a brake or as a dynamometer, and this will be the mechanical load, right? Mechanical load of this machine. Okay, now, so there are a lot, right? But for this experiment, we are going to use only number 1 and number 2. Okay, number 1 and number 2. This is clockwise prime mover brake and counterclockwise prime mover brake. And again, there is also a function there that we can show also here. This is actually corrected torque. We can also show here a not corrected torque by pressing the function button for 5 seconds. This one will have a not corrected torque value. Okay.